guys, welcome back to the second lecture for the 1.1 textbook from the Briggs textbook that we're looking at. So you can read pages 6 through 9, kind of correspond to the lecture that I'm going to do here for you today. And so basically what we're going to talk about are two things. We're going to talk about secant lines, difference quotients, which we talked about last year, and we're also going to review a little bit of symmetry for functions. So getting into it, just as a reminder, when we look at our secant line that we talk about, a secant line cuts through a function in 2 points, so here and here. And when you talk about a secant line, the Latin secare is to cut through. And so that's why we have the secant line, which cuts through the curve. Now, we say 2 points, but it's okay if it hits it in more than 2 points. It's just that you have 2 points of interest that we're going to look at. The 2 points of interest would be our A, f of A. And recall that you input A. Here's your point that has a y value of f of A. And the other point would be B and f of B. And so when we look at that, what we really are calculating when we talk about this secant line and this average rate of change, what we're doing is we're calculating a slope of the secant line, change in y over change in x. So our rise over our run here. So when we take a look at that definition, that rise over run right here is called the difference quotient. And the difference quotient is a difference of outputs over a difference of inputs. Quotient just means fraction. So we used this up quite a bit last year, so we're just kind of going through and talking about it. Now, a couple of things that are important to start paying attention to about what is the behavior of the function when we know things about the average rate of change. And so what we know is if the average rate of change is positive, that the second point must have been an increase from the first point. To get from the first to the second point. Now that doesn't mean that the function actually increased the entire time, but the overall trend is increasing. And the overall trend is decreasing if your average rate of change is negative. Now let's look at an example where we might use this in calculus. Basically we do a lot of problems where we talk about velocity. And velocity, if you will recall, if you're in physics or you've taken physics, you know that velocity has two components. There's speed, which is the magnitude of how fast the car is actually going, and then there is the direction, which way the car is going. So there's a positive and a negative component, and since we're doing north, we might be saying that north is going in the positive direction and that south is going in the negative direction. So we take a look at this. We have that t is going to be our time in hours since the beginning of the trip. And then we usually, and this is just a standard notation, I know that the position function, you might want to call it P of t, you might want to call it D of t for distance, but in calculus, D of t is kind of reserved for something else. So a lot of times they will often call this position function S of t. And so it's going to give us our signed distance from the starting position. So if the car drives north, then your signed distance would be a positive distance. And if the car drove south, that would mean sort of backwards, then that would be a negative direction when we take a look at that. So those are kind of the background of the information that we have in this car example that we're doing. Now, what we want to do when we're looking at this is think about what points are on the curve. So it's driven north for 100 miles and it's a 2-hour trip. So we definitely know that S of 0 is 0. So that's our initial position that we have. We're starting at that starting position. And then S of 2 is 100 miles. So we can then go ahead and calculate our average rate of change by simply doing change in position over change in time. Change in S over change in T. And remember that the uppercase delta is a Greek letter. It just means change in whenever you see that. So we go ahead, we have our nice little difference quotient down here, and we can calculate that for this problem simply by plugging in. And whenever you use an average rate of change, just like we trained you last year in pre-calculus, you must always show a difference quotient, a difference in the top, a difference in the bottom, You must simplify it. So coming down here, plug and chug, get your 50 miles per hour. And we do want to always show units, especially in a real world problem. Knowing the units is going to be important. And the unit in the slope is always going to be the unit of the y value, the s, over the unit of t. Now, when we talk about this and we say, well, what was the car actually doing? How was the position changing? There are many different varieties of what actually is happening. Now, it could have been that your position was changing at a constant rate, which means that it's a linear function. So as your position changes, the car was traveling the same 50 miles per hour the entire time. Now, that may not be true. I mean, an alternate scenario might be that velocity is actually increasing, that the car started with a velocity close to zero because you know you're starting off, and the velocity itself is increasing over time. And what happens then when your speed and you're accelerating, that your curve, notice that the position is increasing, but it's increasing at an increasing rate, which we talked about with concavity and concave up when we're looking at it. But even if you do have a positive average acceleration, that does not mean that the car was always, the position was always increasing as you went. So here's an example where the car kind of overshot the position that they wanted to be in. So they went past it, and then when they came down, that means they were going south. So whenever your velocity is negative or your function is decreasing, like in this little section of the graph right here, that would mean that you would be going south in that kind of idea. So the car was traveling, sorry, I can't get it to not keep putting that there, but the car was traveling north up until this peak right here, and then realized they overshot their destination, and then they were traveling south for that part of the trip. Notice your overall average velocity was still this 50 miles per hour, even though they have a component of speed velocities that are negative because they had to backtrack. It's just they were going really, really fast here, and then they had to come back, and so it balanced out to still be the 50 miles per hour. So average velocity tells us an overall trend, but it does not necessarily tell us, you know, exactly what was happening on that position function when we were looking at it. Now, there are 4 forms of this difference quotient that we're going to be using that you should be familiar with. Now, the first one is the one we just used, and that one is one where you have a fixed interval. You're going to know the x values of a and b, and you're going to know the y values of b and a, or if you don't know them, you're going to have a function formula, a graph, or a table where you can get those values from. All right, let's look at another example. In this one, we're going to do one that's not a time problem, but actually a profit problem. So we have a company, this company is selling these widgets, and we're going to assume that everything produced is sold, and that P is the profit for the company. And they have a nice little formula over here of what our profit is going to be, a little quadratic formula that we're going to be working with. And we want to find the average rate of change of profit between 60 and 90 widgets. So notice that this is form 1 because it's a fixed interval. I know the beginning and I know the end, and I have a formula, and so I'm going to be able to get the y values that go with those values. So quickly just showing you this example. And this is kind of a side comment on this. And a lot of these problems, we may be arguing that the domain should only consist of integers because you really can't make part of a widget. But for the interest of this problem, we're just going to kind of wave our hands a little bit, and we're just going to go with it that the domain, the applied domain that we talked about last time, is going to be 0 to infinity, and we're just going to use that in this problem. All right, so we basically are just going to plug in our 90 and our 60 into our functions. We're going to calculate the difference in 90 and 60, and it's fairly straightforward. The only thing I will caution you is when you are doing your actual algebra for this type of problem, that you do want to make sure, right here in red, the warning, grouping symbols are important. Make sure that you utilize parentheses and brackets so that you know where things like this negative right here need to distribute through the problem. All right, now from here, it's simply just arithmetic. You're just going to simplify, multiply out this down here. Notice they multiplied out that there, and then they very carefully distributed this negative so that all the signs change. And a lot of times, instead of, you could have evaluated P of 90 separately, and then P of 60 separately, and then put them together into the formula, which is perfectly fine. Or you could do what they did here, which is just plug in and use the formula. The nice thing about using the formula sometimes is you start to see things that will cancel out. This is going to be a trend that you're going to see in a lot of these examples, that things cancel out nicely. And then we go ahead and finish it out. And then our units on this, remember our units are the change in the output, the profit, dollars, over the change in number of widgets. So it's dollars per widget when we're taking a look at that. Now, practical interpretation, we're basically saying that on average, okay, I'm going to stress that, on average, if you increase your production level, your profit will increase by $50 per widget. That may or may not happen. Think back to the 3 examples we had on the slide with the car. It may be increasing slower. It might be concave up. It may be concave down. There's different things that could be happening with this function as it kind of works through the problem. But on average, you would gain about $50 per widget. So our total increase in profit, which is simply P of 90 minus P of 60, is going to be the $1,500. We gained $1,500 over the 30 additional widgets. Now, again, that doesn't tell you that, it may be that when you add the first maybe 20 widgets to that, you're gaining a lot more than $50 per widget, but then maybe you start to lose money at that. So the average rate of change is great for getting an overall view, but it may not tell us everything about the problem. This is just an example graph. This one is our profit is increasing at a parabola, so we can kind of see what's going on. We have a nice concave down section. So in the beginning, it's a little bit steeper in the beginning than it is at the end. So we're probably gaining a little bit more than $50 per widget when we start adding the numbers past 60. And then less so much when we get to 90, but we're still gaining. So that's a good thing. Our profit is still increasing on that. Now, if we had been like over here on this side, maybe at 130 or something, then you might have an idea of seeing that your average rate of change would be 0. And you maybe say, don't add any at all. But that doesn't mean you shouldn't add any at all. It means you should investigate a little bit further because you don't know what's happening in between your 2 points that you have. The average is kind of just a snapshot of an overall trend. All right, and then the slope, right? The slope of the orange line, that's my secant line that intersects it in 2 places, and the slope of that line is $50 per widget. All right, let's look at our second form. Our second form, we have a variable endpoint. So I'm going to know A, it's going to be a fixed starting position. A will give me f of A because I will know that. However, I do not know the endpoint. I'm going to leave that as a variable. I'm going to let it vary. That's the idea of trying to look at the trend and pick different values to plug in to see what my average rate of change is depending on how far away I go. So I could pick, 90 and then 120 and then 150 and kind of do a comparison on that. So we're going to leave that as a variable. Now notice that it's f of x minus f of a because you always do end minus beginning. So change in y would be f of x top minus bottom and then right minus left on that. All right, so let's go back to our same example. We're going to repeat this problem using the same formula, except now we're going to leave it in this form too, where we have the variable endpoint. So we're going to calculate it. And when we first plug it in, it looks very similar. This part right here is exactly the same as what we did before. But notice up here, now we have the formula there. So we plug the formula in. Our final answer after we simplify this is going to have x's in it. So it's going to be a formula that allows us to plug in different endpoints and calculate rates of change. Now again, same thing, a little bit of the algebra through this. And I'm putting this up here very quickly, but I'm sure that I trust that you guys are well versed in distribute your negative through, cancel your like terms. You end up here with a quadratic. Now, kind of as a general sense here, whenever you have a quadratic that is negative, in terms of simplifying, pull the negative out because it's easier to factor that when you don't have the negative on the first term. So we've pulled that out, and it's also kind of like pulling out a GCF. If you had a GCF, pull out the GCF so that you can factor it easier. Now, there's a comment about this quadratic that something that will always be true, and this will help you in your factoring. Notice that if I come back up here where I have this whole top part right here, if I were to plug in 60 for x, then p of 60 minus p of 60, of course, would be 0. And so I want to remind you of an Algebra 2 theorem that we also reviewed at the end of school last year called the factor theorem. And the factor theorem implies that if you have a polynomial on the top, so p of x minus p of 60 is just a polynomial, and we got down here to this quadratic, then if you plug a number in, a candidate for a root of that polynomial, if we plug it in and we get 0, then we know that the factor x minus 60 is going to be a factor of that polynomial. So it'll help you in terms of factoring because the x minus 60 has to divide into that evenly, and then it makes it a little easier. You don't have to guess and check as much. You know one of the factors is x minus 60. And so here's the factoring with that. We can cancel and remove the discontinuity, the restriction. Notice we're writing on the side this little exception over here. And then down at the bottom, as soon as my little thing goes away, we get down and we have this formula. And I went ahead and multiplied the negative back through just to make it a little nicer. So the average rate of change from 60 to some unknown endpoint x can be found by using this simple formula, 140 minus x. And so it's still going to be dollars per widget. And now you can just plug and chug if I want different ones. And if I were to plug in 90, then I would still get the same $50 per widget that we had. But this formula may be a little bit more useful in terms of, well, what if I plug in 80 and what happens? And then what if I plug in 130, what happens? And so on. And so we can look at what's happening to the average rate of change away from 60, like maybe in the short term, it's doing pretty well. So if I were to plug in, say, 70, I would be obtaining $70 per widget. Whereas if I plug in the 90, I'm only getting $50 per widget. So you can kind of see a little bit about the interplay of how the function is changing in between the points that you're picking. All right, our third type of form of this difference quotient that we are going to look at, sorry, I'm looking down because my dog is right at my feet, that when we're looking at this, now we have a variable run. So we know A, okay, and this is kind of looking at it in a little bit very similar to what we just did. But what we have here, instead of saying this is the variable, we're going to say that A is known, and of course we know f of A, but this H, this difference in the X, a lot of times it's called delta X, or we like to call it H. This run is going to be what's considered our variable. So our ending value over here, instead of calling it B, we're going to call it A plus H. We've moved over H. Now, it's all going to be the same thing. Everything that I'm showing you with these different forms is doing exactly the same thing, just in a slightly different way. And when we get into calculus in more detail, we'll use all these different forms in different ways. All right, so again, this is going to come up with a formula for us, but this formula is not going to be in terms of X. The second endpoint is going to be in terms of the run, the delta X. And so the H is going to end up being our variable in this problem. All right, let's look at the same example again using this new form. So same formula, except now we're going to be calculating this. See how I have 60 is the A, the starting point. The H is this run that I'm going over, and the bottom, of course, the change in X is going to be H. So we calculate that. Now, same idea, it's a lot of algebra, just got to be careful. We plug in, remember this is composition, so 60 plus H gets plugged in here and here. Then we plug in our 60 over here, and then we start to simplify. So when we take a look at it, we multiply out our quadratic, that's this part right here. We distribute our 200, that's this part right here. And then, of course, we simplify our numbers like there. We do have some cancellation, sorry. The dogs are barking. And you'll notice, and this is kind of the nice thing about this. Let me move myself out of the way here. Look at how much cancels when we're doing that. So it starts out really, really messy. And this is a method that we call the sledgehammer because it breaks everything out into a bunch of little tiny pieces. But then you sweep it all back together and things will cancel out. And that will always happen. And look at how all of these at the end just went away. And so what we have left is this very simple 80h minus h squared over h. And what's nice about that, and we saw this last year, is that when we get to this point, notice that everything that's left in the top and in the bottom still has an h in it. So we're going to be able to factor that out. And when we factor that out, we can remove this h, this restriction again. We put our exception, and now we have this formula 80 minus h. So if we go back to the same problem and we say 90, when we're looking at from 60 to 90, our h would be 30. So I simply would plug in 30 into the h, and so 80 minus 30, I get the $50 per widget that we would have gotten before. Again, it's just a different way of looking at it in terms of having some variables that you can adjust. So now instead of having to plug in an endpoint, plugging in 90, now I'm just saying, well, what if I want to be 30 away from 60? What if I want to be 20 away from 60? What if I want to be 10 away from 60? And so on. And so that also allows us to kind of keep working with this. All right, and then our final form. This is the big daddy of them all. This is where everything is a variable. We don't know our starting point and we don't know our ending point. And so we're going to keep it as the x and the h, that we don't know exactly what's happening as we take a look at this. So this is going to be the most general formula that we come up with, which is the difference quotient. And so we're going to practice with this a little bit, and this is very important for calculus. Now, one comment that I will make before I go and do the example for this one is that I want to make a point that even though all my pictures that I've shown you so far show us moving from a beginning point and moving to the right to get the end point, which would make our change in x, our denominator, positive, that you can actually move backwards as well. And so that denominator can be negative. And so that's the beauty of this. So we can move a point and say move forward and move backwards along the curve and talk about average rates of change for going forwards or backwards. So it's kind of one thing that's out there that makes this even more general. All right, so now let's take a look at same problem, but now we're going to use this most general difference quotient. So now we're going to take this same quadratic and we're going to plug in x plus h, wherever there's an x. We're going to plug in x, which basically means write the formula, and we're going to simplify. So here's our first step. So here's my quadratic with the x plus h here and here, and then the minus p of x all over h. Then we just are going to do some algebra. We're going to FOIL out the quadratic, distribute the 200. Over here, we didn't really have a lot to do. We just brought it down. Next line, we're going to distribute this negative here. That's this one. You're going to distribute this negative right here through the second term. Now, in terms of the amount of work shown, you just have to be careful. You don't need to show every step. I'm just showing you in this example so that you have a very thorough example of step by step. We get to the end, and just like before, a bunch of stuff cancels, so we have sledgehammered it out. Now we're going to be canceling things out. And notice when we get down here to the end, I still have an h here, here, and here. And so what that does is, again, I can do that same process. I can factor the h out. I can remove it. And then once I remove it, then I get this formula at the bottom. So that is the most general formula that you have. And so basically it says that given any starting point and then moving any distance away from that, I can calculate the slope of the secant line or the average rate of change by plugging in those two values. So if we're starting at 60 and h is 30, if I put in 60 and 30 into this formula, I would have negative 2 times 60 minus 30 plus 200. You're going to end up back at the $50 per widget that we had. So these four different forms are going to be kind of interchangeably used depending on what we know and what we're looking for. And some are better for calculus later on. This formula is going to be something that's going to be very useful when we start going from secant lines to looking at maybe tangent lines. And so the idea here is going to be that we sometimes want to come up with formulas that we can use in a more general sense than just plugging in and getting numbers, which is what we did in the first form. All right, now our last thing that we're going to do in this video is we're just going to just recap symmetry, making sure to remind you about symmetry of graphs. So there are three symmetries that we base, special symmetries that we look at in graphs in general. A graph is symmetric with respect to the y-axis whenever you're looking at it and you have the point xy and the point negative xy on the graph. So here's like a little parabola would be an example of something that is symmetric with respect to the y-axis. You could also have a graph that is symmetric with respect to the x-axis. So in that one, we have our point xy and our point x negative y. Now, I will tell you that, of course, if you're looking at this type of symmetry, this symmetry does not exist for functions because this obviously would not pass a vertical line test because it would always have matching points above each other like that. So this doesn't happen for functions, but it could happen in relations, circles, sideways parabolas, hyperbolas, things like that that we might look at later on. Then we have symmetry over the origin. So symmetry over the origin is where you're looking at a point xy and your point negative x negative y down here at the bottom. So no matter what point I pick, there should be a matching point that has the opposite inputs and outputs for that. And when we look at functions in general, then the only two that apply for functions are going to be symmetry over the y-axis and symmetry over the origin. So even symmetry, here's our property. We're basically saying that the x's were opposite, but the y's were the same. So when I put in the opposite x, the y, also known as f of x, is exactly the same. So if we have another function, here's an example showing not a parabola, but this is a fourth degree polynomial. Here are my, and it has to be for all points. Just realize that. Just because 2 points match, it has to match for all points. So this point right here would match that point over there and so on. Now the test that we would run from that, how do you prove that algebraically that a formula is going to be even symmetry? You plug in negative x. So you take your function formula, you plug in negative x, we simplify, and if what you get after you simplify is the original function, then you get to conclude, therefore that function has even symmetry, and that's what you expect to see on the graph. If I do an odd function, then in that one, we plug in the opposite of the x's, but notice that the y values, f, are also opposite of each other. So both the x's and the y's are opposite. Here's an example of a nice rational function that has odd symmetry. So, if you look at, there's matching points here and here, matching points here and there, and so every point has a matching point that has the opposite x and the opposite y. Here's my formula for it, and again, showing it, you would first take this formula, we'll call it h of x, plug the negative x in, down at the bottom, I simplified, and I immediately looked at this, and then I looked at what I had over here, and I said, hey, they're not the same, not yet. So I start doing some manipulation, and one of the things you'll do is you'll factor out a negative, and when I factored out this negative, know that a negative on the bottom is the same as moving it to the front. And then you'll realize that this is exactly the opposite of what you started with, and then you get to conclude that it's odd. And then we'll finish up with, here's an example of a function that has none of these special symmetries. That doesn't mean that there might not be a point somewhere in here that there is rotational symmetry about. But when we talk about symmetry in functions, we're really talking about the two specials, even over the y-axis, odd over the origin. So showing that we don't have symmetry in a function algebraically, we plug our negative x in over here, I simplify it, and I go, well, that's not the same as g of x, so it's not an even function. And then when I factored out that negative, I then again compared it again, and you'll see that because of the plus here and the minus there, it's not the opposite of the original function, so it's not equal to the opposite of g of x either, which basically means it's neither. So we would conclude it has no special symmetry when we look at it. All right, so that wraps up this recap of difference quotients and symmetry. And so you should be ready to begin the next activity that we have in class.